In previous videos, we've talked about the first derivative and how we can use the first derivative to tell us about where a function is increasing, where it's decreasing, where it has relative maxima and relative minimum. So now we're going to switch gears and talk about the second derivative. The second derivative gives us information about things called concavity and points of inflection. So first let's talk about concavity. First, there's two kinds of concavity. There's concave up, that looks like the U in the word up, and there's concave down, which looks kind of like the N in the word down, or at least a lowercase n. So that's kind of the informal way to remember it. Up looks like a U, down looks like an N. But the formal definition is also here. A function is concave up whenever its graph lies above its tangent line. So if I were to try to draw tangent lines here, no matter where I draw my tangent lines, no matter what spot I pick, my graph is always above that tangent line. Whereas for concave down, if I draw the tangent line, my graph is below the tangent lines. So you can tell whether it's concave up or down based on the tangent line. And then points of inflection are simply points where the concavity changes. So a easy example would look something like this. Right here we would have a point of inflection, because on this side we would be concave down and on this side we would be concave up. So it asks us to find where this function is concave up or concave down and where it has points of inflection. If you know how to do the first derivative test, or you watch that video, then you should have a pretty good idea of how to do this. It's almost the exact same process, we just do it with the second derivative instead of with the first derivative. So my first task is to find the second derivative. And we come to 12x squared minus 24x. We set it equal to 0, and we can factor a 12x out front. That gives us 0 and 2 as our, they're not technically our critical numbers because they're coming from the second derivative instead of the first derivative, but they work the same way. It's where the second derivative equals 0 or doesn't exist. So I like to call them the potential points of inflection. Just like our critical numbers are our potential maximums and minimums, these are potential points of inflection. So I set up a chart exactly like I did before. Negative infinity to 0, 0 to 2, 2 to infinity. And, like before, I need to pick test points, but this time I plug them into the second derivative. Remember, you can use this version of it or this version of it. Either way will work. I'm going to choose to use the bottom one, but let's see, if I plug negative 1 in, I get negative 12 times negative 3, so that is a positive. If I plug positive 1 in, I get positive 12 times negative 1, so that's a negative. If I plug in positive 4, I get all positives. And it turns out that when the second derivative is positive, the original is concave up. And when the second derivative is negative, the original is concave down. So now we've established where the graph is concave up and down and what intervals that takes place on. The last thing to do is look for points of inflection. Well, as long as the concavity changes, those places are points of inflection. So at 0, we do have a point of inflection because it does change here from up to down. And also at 2 because it changes from down to up. So as long as those are alternating, every single spot's going to have a point of inflection. It's only if you get, say, an up followed by another up that it would not be a point of inflection. So as long as it changes from one point to the next, up to down or down to up, it's a point of inflection. So I'll just try to make this a little even more clear. If we have, for example, had an up and a down like that, 0 would not be a point of inflection in that case because there was no change here from up to up. But 2 would be because it went from up to down. Okay, just one more example with this, since it's really similar to the first derivative test. That should be sufficient. Here, if you want, you can bring the x squared plus 3 up top and raise it to the negative 1 and then do the chain rule. I'm going to prefer to do the quotient rule, but that's just my preference. You can do it either way. f prime, sorry, I don't know where I got x. F is 6, so f prime is 0. G prime is 2x. So I get f prime times g is just 0 minus f times g prime all over g squared. So I get negative 12x over x squared plus 3 squared. Now here's the yucky part. We have to find the second derivative. That's just the first derivative we found. We have to find the second derivative. So we have to start that process all over again. The top is negative 12x. The bottom is x squared plus 3 squared. F prime is negative 12. G prime, we have to use the chain rule. So we get 2 times x squared plus 3 times 2x. Alright, so now let's start working on that. Second derivative here. Negative 12 times x squared plus 3 squared minus, I'm going to need more room, going to go ahead and move this down, f times g prime. So we get negative 12x times, I'm going to go ahead and combine these, 2 times 2x is 4x, and then x squared plus 3, all divided by g squared. So since that squares a squared, we end up to the fourth. Well, if you notice, all three pieces there, the two on top and the one on the bottom, have an x squared plus 3 in common. So I'm going to cross one out for each one. That one goes away completely. This one will now just have 1 left. This one will now have 3 left. So now I can simplify the top, negative 12 times x squared, negative 12 times 3, and then negative 12x times 4x with a negative out front makes positive 48x squared. And then combining our like terms on top, I get 36x squared minus 36. And then we pull 36 out front. Okay, now we're finally ready to find those potential points of inflection that'll help us build our chart. I know, it's a really long problem, but got to do what we got to do. So if you look at the top equation, both 1 and negative 1 will make those 0. So that's two critical numbers. And actually there's nothing that will make the bottom 0. There's nothing that will make the bottom 0 because there's no way to make x squared equal to a negative 3. And that's what it would take. So we just have two potential points of inflection to create our chart with. But after all that work, that's actually kind of convenient. That's all I have to worry about. Okay, so f double prime, we need to plug test points in there. So I'm going to pick, say, negative 2. Well, if you notice, if you try plugging stuff in the bottom, it's always going to be positive. Because if you square it and then add 3, it's always positive. So you really just have to focus on the top. If I plug negative 3 in here, negative 3 squared is positive 9. 9 minus 1 is a positive. If I plug 0 in that x, I get 0 minus 1, which is a negative. If I plug positive 3, 3 squared is positive 9. 9 minus 1 is a positive. So f will be concave up, concave down, and concave up. So we do have points of inflection at both 1 and negative 1, because at both of those spots the concavity changes.